Okay, break from the normal distribution. We'll learn a new distribution. Right? You've seen the normal before. You kind of heard of this, the central limit theorem of thing before. So let's learn about something new. And if you looked at the bonus problem that I put out last week, it was relating to one of the things in here. I had you find the mean and the variance of the gamma distribution. So anyway, we're not going to derive it here. We'll just see what it is in a second. But let's start learning about something. Before we get to the gamma distribution, we have something that is going to be useful in this distribution. It also pops up in other areas called the gamma function. What is a gamma function? Well, let's recall what factorials are. I'm sure we've all seen before n factorial, right? If you have a non-negative whole number, n factorial, like 3 factorial, is what? We start with 1 and multiply by all numbers up to that. So 3 factorial will be 1 times 2 times 3, etc. But that's if you have a whole number. So what if you don't have a whole number? Right? What if n is like 2.3? What is 2.3 factorial? We don't really have a definition for that, or at least as of yet. So that's actually what this gamma function is. As weird as it might be. So a generalization to factorials is this gamma function. So what is it? So gamma, it's a Greek letter gamma, capital gamma of alpha. So the number goes in there for alpha being also positive, is equal to this integral. So we integrate from 0 to infinity of x to the alpha minus 1 times e to the negative x dx. So compute that, and that's your gamma of alpha. Right? That's the equivalent to a factorial. So bear with me. What we're going to do is we're actually going to work out one of these problems, but we're only going to have to do it once. Right? So we're going to do a little bit of work, and then we arrive at an easy result, and then we get to use the result after that. So let's take a look. So let's try gamma of 2.3, right? What is 2.3 factorial? So according to this up here, it'd be the integral from 0 to infinity of x to the alpha minus 1. So x to the 2.3, there's the alpha, minus 1. And I'm going to leave it like that. I know you can subtract that in your heads, but I'm going to leave it written like that just to accentuate what we're doing. Times e to the negative x dx. Okay, now if I was to do this long ways, right, this x to a power times e to a exponential, or e to the negative x, that's a perfect setting for integration by parts. Now I can't do my table method. Why? Because the table method, I would set x, the power of x to the u, but I have to keep taking the derivative and get a 0. I would never get a 0 here. If I took the derivative, I get x to the, see, this is really x to the 1.3. If I took the derivative, I take away 1, I get x to the 0.3. Derivative again, I get x to the negative 1.3. And it only go into the negatives. I never get 0. So bear with me. I'm going to do this the long way. So I'm going to let my u be x to the 2.3 minus 1. My dv, e to the negative x, dx, sorry. Because what are we trying to do? We want to set up uv minus integral v du. So u is the power of x, dv is e to the negative x. So du, take the derivative here, I have 2.3 minus 1, that power comes out in front, times x to the 2.3 minus 2 power. Let's subtract 1. And then I'm squishing this in, and then v is just e to the negative x, or negative e to the negative x. du, v, u, dv. So u times v, I have, say, a negative x to the 2.3 minus 1 times e to the negative x. Now, when I go to write this, though, this is actually inside this integral where I actually have these limits. So this first part could go ahead and just be evaluated from 0 to infinity. And then would be minus this integral from 0 to infinity. Let's see, what do we have? So integral v du. So v du Actually, I'm going to take this negative and this 2.3 minus 1 to the outside. So this will be a plus 2.3 minus 1 the outside of the integral, but the integral would go from 0 to infinity of the rest of our v du, which would be what, x, the 2.3 minus 2 times e to the negative x dx. I'm sorry, got sloppy here. Separate that. Okay. As messy as that might look, if it's just kind of basic, makes sense, a basic integration by parts problem. So here, I can evaluate the first part, right? The integrating is done. So as limit goes to infinity, right, I have e to the negative x. So I have e to the infinity on bottom. Put my negative out in front. So this whole thing would go to 0. And then minus plugging in 0 for my limit. X out in front, being multiplied by 0, would also be 0. So the whole first part just goes to 0. And now what am I left with? This is why I did not subtract the 1. It's about to become clear, hopefully. So I have 2.3 minus 1 out in front times the integral from 0 to infinity of, let me write it as x to the 2.3 minus 1 minus 1. Minus 2, I'll break it up, sorry. Minus 1 times e to the negative x. All right, like I said, we're gonna do a little bit of work to save ourselves work in the future. Does this look familiar?
It's the same formula.
Sounds new to me. Well, let's look at the form. X to a number minus 1 times e to the negative x. X to a number minus 1 times e to the negative x. This is now equal, by definition, gamma of what? This is now my new alpha. Right, the number subtracting 1. So this entire thing is equal to gamma of 2.3 minus 1. But we have this number out in front too. 2.3 minus 1. Okay? So what happened? I actually get a number. Are we done? Well, we're going to be done for now. So gamma of 2.3, right? Go through everything. It ended up being 2.3 minus 1 times gamma of 2.3 minus 1. Okay? Now this is useful because we can keep going, but I'm going to stop with that for now here. That's kind of our first formula. Oops, sorry. So gamma of alpha can be reduced or simplified to alpha minus 1 times gamma of alpha minus 1. That's exactly what we just did here. So every time you go through that math, whatever number you start with, I go through our integration by parts, you're going to end up with that number minus 1 and then gamma of that number minus 1. So we can take it as a generality. Okay, we're going to use that in a little bit. Now another thing is, well, what if you have a positive whole number? What if you have n? I'm not going to derive this one, but gamma of n, if it's a whole number, is just n minus 1 factorial. Right, so gamma of 3, for example, is quite simply 3 minus 1 factorial, or 2 factorial, I'm sorry, or 2 factorial, which is 2. Okay, so this is kind of why I said, like on the quiz on Friday, some of the problems might go quicker. So if I ask you on Friday, what is gamma of 4? Should be able to be pretty quick math to do. Okay, so we have these two properties. And one more over here. I don't have time to derive this. I think it's in the book someplace. We're just going to take it and go with it. So gamma of a half. We get a special relation here. Gamma of a half comes out to be equal to square root of pi. Right. Now that's not something we use in and of itself, but we use that in a lot of cases to simplify things. So if I had gamma of say 2.5, right? I actually want to find a value with this. I can combine numbers 1 and number 3 here. Because start off with this. What is this equal to? This is equal to, this is my alpha. It's equal to alpha minus 1, which would be 1.5, times gamma of alpha minus 1, times gamma of 1.5. You might think, well, we didn't really go anywhere. Well, I can keep reducing this, right? Now I just move over. What is gamma of 1.5? Well, I have 1.5 here times, all right, this is my new alpha, so it's going to be alpha minus 1, 0.5, times gamma of the alpha minus 1, 0.5. So now what do I have? 1.5 times 0.5, then gamma of 0.5 is square root of pi. So at least if my alpha is 0.5 something, I can reduce it to something I can calculate pretty easily. Okay, so not going to plug that in the calculator. We'll just leave it like that. We'll take it as that. Okay, so we have just a couple minutes left. Let's do these two problems. Then I will let you go. All right, so real quick, gamma of 6. That's a whole number. So that is just gamma of n is n minus 1 factorial. So 6 minus 1 factorial, or 5 factorial, or 120. Done. Okay. Next one. No idea what this is. Well, that's okay. If you look on the inside, it's at least sort of similar to this gamma function. Right? So when I see this, that's what we're going to try to do. Relate this to the gamma of alpha, which is what? The integral from 0 to infinity. My first hint is I see that. And I have x to the alpha minus 1 times e to the negative x. Kind of like that. All right, so what do I have? Well, first, constants, I can just bring this constant to the outside. So I have 9 times the integral from 0 to infinity. Will be a little bit tricky. X to the 4 is the same thing as x to the 5 minus 1. I'm trying to set it up to make it look like this. Then e to the negative x is just e to the negative x. So that's actually 9. Then what is this? This is actually gamma. The gamma function of my alpha would be 5, right? The alpha, the thing being the minus 1, is really 9 times gamma of 5. Okay, almost done, which is 9 times what? What's gamma of 5? 4 factorial. So 9 times 24. Okay, and 216 would be our answer. Okay, and right on time, we'll stop there. So the last little bit we have to go, so we're actually going to learn what the gamma distribution looks like, and then get into the other two parts. So there's a part 2 to this note, so we'll finish this and then roll into the part 2 on Wednesday.